Hi, welcome to this video on binary operation where we'll be talking about the commutative property. In earlier videos, we've looked at the meaning of binary operation and then we've looked at the closure property. If you've not seen the videos, you can do well to watch them before coming here. Alright, so for commutative property, what exactly does it mean? We're saying that if A delta B is equal to B delta A, where A and B are elements of real numbers, and the binary operation is commutative. What does it mean, A delta B being equal to B delta A? It simply means the order of arrangement doesn't matter. So if you decide to take A first and combine it with B, it's going to give you the same thing as when you combine B first with A, then definitely we can say such property under that operation is said to be commutative. Now, basic commutative properties in maths are addition. So we say additions are commutative. What does it mean? So it means, let's say I have two numbers, two real numbers, 3 plus 4. Now with 3 plus 4 will be the same thing as 4 plus 3. If this is true, then definitely I can say addition is commutative. We can say this one 3 is first, then followed by 4. While for this one 4 is first, then followed by 3. So 3 plus 4, what do we have? We have 7. And 4 plus 3, what do we have? Again, we have 7. All right. Now, so this can bring us to a conclusion that addition is commutative, or addition of real numbers is commutative. All right, so how about we take another operator? So let's say multiplication now. So let's still use the same number, 3 multiplied by 4. So will this be the same thing as 4 multiplied by 3? Again, 3 times 4, this gives us 12. 4 times 3 will also give us 12. So you can see that the order doesn't matter for multiplication also. So again, we can say multiplication of real numbers is also commutative. Now let's try for subtraction. So subtraction, same thing. So 3 minus 4, will this give us the same thing as 4 minus 3? Will it give us? So 3 minus 4 gives us minus 1. And 4 minus 3 gives us 1. So you can see that minus 1 is not equal to 1. So definitely 3 minus 4 is not equal to 4 minus 3. So what is that telling you? So when you want to use the operator, subtraction or negative, then the order matters, because whichever one comes first determines the result that you are going to be having. Okay, so subtraction is not commutative, and also division is not commutative. So if we said 3 divided by 4, is it the same thing as 4 divided by 3? Of course, definitely not. So 3 divided by 4 is 3 over 4. And 4 divided by 3 is this. So these are not equal. So addition and multiplication are commutative, while subtraction and division are not commutative. Or let's rephrase that. Addition and multiplication of real numbers are commutative, while subtraction and division of real numbers are not commutative. All right, so let's look at a much more refined definition, and then I'll give you a nice trick to know. So let's say you are given a table, and then you are asked to find whether the data you are given is commutative or not. How do you determine such thing? So let's look at our first example, and then we'll see where we go from there. So we're told that a binary operation is defined as x delta y equal to x plus y minus 2xy. And then we are asked whether the operation is commutative. We're asked whether the operation is commutative. Maybe looking at this, you'll be thinking, but this question is not complete. There's nothing you can do about it. But no, there's actually something you can do about this. Remember, for a binary operation should be commutative. So what are the two letters we're saying here, variables, x and y? So it means x delta y must be equal to y delta x. Now, if this is true, then definitely we can say that the operation delta is commutative. Now already the question has given us x delta y as x plus y minus 2xy. So let's try and find y delta x and compare them and see whether it will be the same thing as x delta y. If it is the same thing, then we can say x delta y, or the operation rather, delta is commutative, given that it has been defined by x plus y minus 2xy. So y delta x, now again, what do we do? So we'll come back to this operation. We let y to be x and x to be y. So this time around, we have y plus x minus 2yx. Now, of course, since we've done, what's it called? Since the earlier example, we didn't know that addition is commutative. So the order doesn't matter. So y plus x is the same thing as me saying x plus y. Of course, subtraction is not commutative, so we leave subtraction the way it is. And then you can see y and x are being multiplied by each other, or to each other rather. So again, this also is commutative. So I can decide to bring x first and then write my y. So this is y delta x. So you can see that y delta x and x delta y. This is x, this is x, this is plus here, y, minus 2xy, 2xy. You can see that x delta y and y delta x are equal. So definitely we can say the operation delta is commutative. So quickly, let's look at the second example. So we are told that if A star B is equal to or is defined as 2A minus B, first we are asked to evaluate 4 star 2. Secondly, we are asked to evaluate 2 star 4. And then we are asked for our observation in our evaluation whether the operation star is commutative. Okay, so without wasting much time, so this is A star B. So A star B is given as 2A minus B. So for the first question was asked to evaluate 4 star 2. So again, assume or let 4 to be A or A to be 4 and B to be 2. So anywhere I see A, I want to write 4. So 2 in the bracket of 4 minus my B is 2. So 2 times 4, that's 8. 8 minus 2, so this is 6. Now this is the first part. For the second part, 2 star 4, 2 star 4. So again, my A this time around is 2. So I have 2 in the bracket of 2 minus my B is 4. So minus 4. So 2 times 2, that's 4. 4 minus 4. So this is equal to 0. So you can see that 4 star 2, after evaluation, using this rule, we're having 6. And 2 star 4, after evaluation, using the same rule, we're having 0. And the question is asking, is the operation star commutative? So the answer is no. So the operation star is not commutative underneath this rule. I hope this makes perfect sense. All right, so lastly, what if we're given a table? So what if we're given a table? So most of the times your questions might not come like this. You might be given a table that looks like this. So let's say you're given 3 members, A, B, C. So it might not just be 3, it might be 3, 4, 5, 6, wherever. So but let's just stick with 3 for the sake of simplicity. So A, B, and C. Now, for this table to be commutative underneath any property, whether star, whether delta, O minus, O dash, O subtract, and so on and so forth. For this to be commutative, then the leading diagonal, the values you're having, or the elements have to be reflected along the leading diagonal. So what do I mean? So let's just assume random value here. So this is B. So let me just say maybe, okay, so this has to be A. Let me say this is C and this is A. Now this is my leading diagonal BCA. You can see this line that is coming here. So we're saying that the element has to be reflected, just like standing in the mirror. So you can see that A is standing in front of this leading diagonal here. So definitely the value I'm having here has to be A. If the value I'm having here is, let's say, C, after standing in front of BCA, it must mean that the value that will be here will also be C. And lastly, if this is B, then definitely after standing in front of the leading diagonal, this line here, and this also would be B. So this is how you can tell if what's it called, an operation is commutative when you are given a table. So when you are given a table, the elements, once the elements are reflected about the leading diagonals, then definitely we can say that the binary operation star delta whichever it is said to be commutative. All right, so this is all I have for you for today and for this class. So do well to like, share, and subscribe if this video has been helpful. And in our next class, we look at the property, associative property. Thanks for watching. God bless, and bye bye.